Welcome back. Today we're looking at a story that proves just how razor-thin the line is between a perfectly routine day and an absolute catastrophic disaster. I mean, we place an incredible amount of trust in the massive flying machines we board all the time, right? We just sit back, relax, and naturally assume that the hundreds of thousands of individual parts holding the whole shebang together have been rigorously tested and perfectly assembled. But as you'll see in this explainer, the nightmare we're about to unpack, it wasn't kicked off by a bomb or a violent storm or some massive unpredictable structural collapse. No way. It actually started with a tiny, seemingly boring administrative error. We're going to see exactly how a catastrophic physical failure was born from nothing more than a piece of paper and a handful of the wrong screws. Let's jump into Part 1, Terror at 34,000 feet.
To truly understand the stakes of this engineering flaw, we really need to start directly inside the cabin at the exact moment of explosive decompression. I want you to truly picture the scene for a second. You're cruising smoothly at 34,000 feet. Everything is completely normal. Then, the cabin lights flicker, just once. A fraction of a second later, a tearing, metallic groan echoes through the fuselage. It's a sound nobody on board has ever heard before. Suddenly, the temperature drops to well below freezing. Hurricane-force winds instantly whip through the cabin, and it's accompanied by the absolutely deafening roar of jet engines and rushing air. Oxygen masks aggressively drop from the ceiling. Passengers are grabbing their armrests, literally frozen in shock as the sheer sensory overload hits. And when you look out the window, a massive section of the airplane's skin has simply vanished into thin air. It isn't dented, it isn't buckled, it's just violently gone.
11,000 feet. That is the raw, terrifying data of this event. That's exactly how far the plane violently lurches and drops in under a single minute. Just imagine the sheer terror of that plunge. Up in the cockpit, the pilots are fighting controls that suddenly feel entirely wrong, like they're almost dead in their hands. They're struggling to communicate through oxygen masks over the deafening roar of the wind, frantically battling the broken aerodynamics of a crippled machine just to bring the aircraft down to a breathable altitude as fast as safely possible. Every single second is an absolute fight against gravity and structural collapse.
Okay, so let's dive into the reality behind all this chaos. The crucial point here is that this terrifying event wasn't caused by severe weather pushing the airframe past its limits. It wasn't a malicious attack either. The absolute nightmare that the passengers and crew were enduring up there was caused by a butterfly effect that started years earlier, literally sitting in a tiny drawer of a parts warehouse miles away. It was just a handful of the wrong screws. They were installed on a completely random Tuesday by a worker who was simply following a sheet of paper. But that piece of paper was fundamentally flawed long before he ever laid hands on it. The disconnect between a quiet, mundane factory warehouse and the absolute terror at 34,000 feet is exactly what makes this failure so incredibly chilling.
Moving right along to our next section, the anatomy of flight.
To truly grasp what went wrong here, we need to establish a baseline for the engineering. You see, an airliner fuselage isn't just one solid, impenetrable metal tube. It actually acts much more like a skeleton. It's a cage made up of vertical ribs and horizontal stringers, all wrapped tightly in a super thin aluminum skin. Because the air outside at cruising altitude is extremely thin, and the air inside the cabin is artificially pressurized to be thick and breathable, that internal air pushes outward in every single direction with immense force. So this means the entire fuselage actually inflates slightly, almost like a giant balloon, during every single flight. And this constant microscopic expansion and contraction, that creates metal fatigue. It's the quiet, invisible enemy of every flying machine.
Think about the typical life cycle of an airplane for a second. It goes through this 4-step breathing sequence on every single trip: climb, cruise, descend, and land. It inflates as it climbs to altitude, it holds that immense tension during cruise, and then deflates back to normal pressure upon landing. Thousands upon thousands of times over an aircraft's lifetime, it repeats this exact breathing sequence. And the thing is, aerospace engineers know this happens. They deeply anticipate it. They know that every single cycle stresses the metal just a little bit more, which is exactly why strict structural limits and design safeguards exist in the first place. The plane is explicitly designed to be strong enough to withstand this heavy breathing for decades.
Which brings us to our next part, one fatal number.
So now let's zoom in on a highly specific part of the plane called the lap joints. Imagine interlacing the fingers of your left and right hands together. That overlapping connection is essentially what a lap joint is on an aircraft's aluminum skin. They're overlapping seams held together by highly specific fasteners designed to stop the skin from tearing apart under all that outward pressure. But here is where the original perfectly safe engineering intent collides with a seemingly minor administrative change. You see, a revised set of instructions was issued to the factory floor just to make assembly faster, but as we all know, faster doesn't always mean safer. This revised blueprint slightly altered the diameter, depth, and spacing of the fastener holes, and doing that left the aircraft with far less structural margin. The fasteners were no longer gripping those interlaced layers tightly enough. It fundamentally altered the physics of the connection, turning a massive, inherently strong joint into an incredibly weak one.
There's a quote that perfectly captures this. A tiny human calculation error, repeated thousands of times across an entire fleet, can bring down a machine. This profound realization pretty much sums up the brutal reality of systemic failure. Nobody on the engineering review board bothered to run the complex long-term fatigue math for this slightly weaker lap joint. It completely bypassed deep scrutiny because, well, on paper it looked completely reasonable. It was just a minor change in hole spacing to speed up the manufacturing line. But because of this totally unverified assumption that minor changes don't affect overall integrity, this tiny calculation error was copied exactly as drawn, stamped for approval, and built into thousands of airplanes across the entire fleet.
That leads us directly into the next phase, the breaking point.
Let's shift our focus to the passage of time here. We're going to walk through exactly how this invisible, microscopic flaw developed entirely unnoticed over years of passenger service. In year 1, routine flights begin. The plane breathes in, breathes out. Everything seems absolutely fine. But by year 3, while the planes flew their normal, totally uneventful routes, the repeated stress on those weaker joints really started to take a toll. Hairline cracks. We're talking microscopic fractures smaller than a single grain of rice were silently growing inside those weakened seams. Fast forward to year 5, and scheduled maintenance inspections are happening across the fleet, but those hidden cracks are completely missed. The silent ticking clock of metal fatigue just keeps going. Until finally, we hit year X, the fateful day of the structural failure.
Now, the really tragic irony of this entire timeline is that routine maintenance inspections are heavily mandated specifically to catch exactly this kind of slow-growing damage. So how on earth was it missed? Well, this reveals a massive organizational blind spot. You see, inspectors and mechanics equipped with flashlights and testing gear only look really intensely where the engineering data tells them to look. And the engineering department? They never flagged this specific revised lap joint as a high-risk area. A mechanic simply cannot fix what the manual doesn't explicitly warn them is broken. You essentially had two completely separate silos, engineering and maintenance never fully communicating with each other. The cracks were literally growing in a bureaucratic blind spot.
And this brings us to a terrifying physics concept known as critical length. When a microscopic crack forms in metal, it usually grows incredibly slowly, right? Taking years to expand millimeter by millimeter with each pressurized flight cycle. But there is a distinct mathematical threshold. The absolute moment that a crack hits its critical length, it stops creeping and it instantly runs. In a fraction of a single second, the crack tore through the remaining aluminum. The weakened metal completely let go. The highly pressurized air inside the cabin suddenly found its escape route, and the skin violently ripped open in mid-flight. That's what triggered the terrifying decompression we started with.
Miraculously, and honestly thanks purely to the incredible skill of the flight crew, they managed to wrestle the crippled aircraft down to a safe altitude and complete a seriously harrowing emergency landing. The passengers walked away from what easily could have been an unavoidable tragedy. But the absolute second the wheels touched the runway and the engine spooled off, the investigation kicked into high gear. Experts arrived on the tarmac immediately, asking one burning question. Why did a highly advanced machine, built to such strict, exacting standards, break wide open in the first place?
Section 5. Rules written in blood.
By examining the freshly fractured metal under extremely powerful scanning electron microscopes, investigators can actually read the precise growth pattern of a crack. It's fascinating. It looks almost exactly like the rings inside a tree trunk. Each microscopic ridge represents a single flight, a single pressurization cycle. This meticulous forensic process proved beyond a shadow of a doubt that this wasn't some sudden break from a massive impact or a freak storm. No, the metallurgical tree rings showed a slow, cyclical fatigue that had been building for years. And when engineers traced that fatigue straight back to its origin point, it led right to the fastener holes and ultimately straight to those mismatched, revised blueprints. The paper trail of the disaster had been there the entire time.
The aftermath of this investigation completely shifted the aviation industry. I mean, it was a true paradigm shift in how we build and maintain aircraft globally. Mandatory joint inspections were immediately rolled out worldwide. The entire affected fleet was instantly grounded until every single overlapping seam could be structurally verified. But the most crucial change was breaking down those dangerous organizational silos we talked about earlier. Regulators demanded strict, continuous coordination between the people who draw and design the planes and the mechanics who actually fix them. Rigorous fatigue testing became the absolute norm for every component, and that old dangerous assumption that a minor production change to speed up a factory line needs no structural review, that was permanently retired.
Aviation safety is not built from good intentions. It is built from failure. I want to let that profound statement sink in for just a moment. The ultimate takeaway from this explainer is that our modern aviation safety net isn't just theoretical. It's deeply reactive. It's built from failure, examined honestly, and ruthlessly corrected so it is never, ever repeated. Every single torque specification on a bolt, every required inspection interval, and every mundane line on a maintenance checklist exists because an aircraft, somewhere, paid the price first. Deadly mistakes are translated into the unbreakable rules that protect the very next flight.
I'll leave you with a final thought to bring this all together. Think back to that tiny drawer of screws and that single, flawed piece of paper. The line between a perfectly routine flight and an absolute disaster is held together by incredibly meticulous engineering and the harsh, unforgiving lessons of the past. So the next time you board a flight and hear that heavy door seal shut, think about the immense, invisible safety net of rules and microscopic inspections you're relying on. It's pretty wild to think about, right? If you want to understand the fascinating, hidden details that keep our complex world running safely, make sure you subscribe to The Explainer for more. Thank you so much for exploring this with us today, and I'll catch you in the next one.